Okay, should I wait? Or can I just start?
I'm just Wysocki. His work is called Causal Decision Theory from the Probabilistically Blind. He comes from the University of Pittsburgh. Tom, you have 30 minutes for your presentation, and then Óscar and Monroy will comment on it. So, whenever you're ready.
Awesome, thank you very much. Yeah, let me just share my slides. Good. You can see the slides, right?
Not yet.
Not yet.
Oh, that's weird. I am sharing.
Yeah, we can see them now.
Oh, that is. Okay, wait. What does it? Let me share that again. Start sharing, and then I want to do this one, and then I want to do this one. Okay, can you see the slides?
Not yet.
Okay, maybe it will come in a second because you already did.
No, we'll see.
Okay, nice. And you can see just the slides. You cannot see my comments or anything, right?
Yes.
Okay, good, because I can see the presenter view. That's all. So it's always like, yeah, online is always, I have to make sure that everything is working. Okay, good, 30 minutes. So let's just run through it. Thank you for having me. And yeah, for me, it's 10, like actually I'm in Europe, so it's 10:30 p.m. They will try to be as energetic as possible given the time. Good. So we'll be talking about a new version of causal decision theory, one that doesn't require probabilities. And slides should be like changing. You guys can see the changing slides, right?
Yeah.
Okay, good. Thank you. So I will quickly briefly motivate the theory, why we need a theory like that. Then I will introduce this causal framework that I developed. It's a more general framework. It's not exactly about decision theories, but the theory uses it. Then I will introduce the actual causal decision theory and then apply it to maybe some infinite cases if we have time, just to show you how it works and what it can handle that other theories cannot handle. Motivation, very briefly. So a classic causal decision theory relies on expected utility, utilities of outcomes weighted by the probabilities. So for those who are maybe not that familiar with this, it works something like that. Let's say you're deciding whether to have a pizza or spaghetti, and you know that you like pizza more, but maybe pizza also gives you some stomachache, and so you'll calculate the probability of the stomachache and how bad it is, and you versus like how much you like the pasta, and let's say like 20% probability that you will get the stomachache, and that gives you certain disutility, like -5 points to your well-being. But if you don't get the the stomachache, then it's like +10 points to your well-being. And if you get pasta, then maybe, you know, there's no probability of getting a stomachache, but it's not that great. So we just +3 points. And you calculate expected utility of one choice, the other choice, and if the expected utility, so the probability of all outcomes times the how much you value those outcomes. If the expected utility of, let's say, pizza is higher, let's say 10 happiness points, and only 8 happiness points for pasta, then you will go with pizza. That's how it works. And here is where you cannot, but it's a very rich and classic theory. There is a huge literature behind it, but it sometimes cannot be applied. So here is where it cannot be applied. So sometimes it's practically impossible to ascribe probabilities. Think of historians that want to evaluate whether it was, it was rational of the French to invade Mexico, for instance, right? And they probably don't want to calculate probabilities exactly and expected utilities of like successful versus unsuccessful invasion, they might just want to think in terms of what was possible, for instance. Right? What's worse, sometimes it's in principle sometimes it's in principle impossible to ascribe probabilities. So, for instance, if you have a lottery with infinitely many outcomes and none of the outcomes are more or less probable than any other outcomes, then it turns out that you cannot ascribe probabilities to those outcomes. Is basically there is no mathematical function that satisfies probability axioms exist that could describe this lottery, right? And finally, sometimes it seems normatively wrong to ascribe probabilities. So let's say if you have a veil of ignorance reasoning, like erosion reasoning, you want to just reason about the regime that you want to design. You don't want to take into account like how likely it is, for instance, for someone to be born without legs, because then you can bet against being born without legs, right? All you want to reason with is that it's possible, but maybe you don't want to reason with how likely that is, right? So maybe in those cases, we don't want to use standard utility theory with probabilities, right? In all those cases, we need a new causal decision theory, and here is one, right? Good. Just to sum up, we need a new causal theory wherever we don't want to or can't or shouldn't rely on probabilities. Good. So here is a causal framework that is non-deterministic. It's not a deterministic causal framework. Things may or may not happen in it, but it doesn't use probabilities. And then I will use it to construct the theory. So here is a motivating case. Daedalus only may succeed if he jumps off the tower, but if he doesn't try, he will stay in prison forever. Minus will be furious, and if and only if Daedalus jumps, and Daedalus may but didn't jump. Those are three counterfactuals about the situation. Here is how we describe this situation in terms of causal models. So variable values represent atomic events, and structural equations represent direct counterfactual relationships between those events. So for this particular case, here is how it would look like. J is 1, so you have variable J, whether Daedalus jumps, J is 1 if he does, J is 0 if he doesn't. E is 1 if he escapes, E is 0 if he doesn't, and F is 1 if Minus is furious, and F is 0 if he is not. That's just the description of the events and the scenario. Here are the counterfactual relationships between them. So first of all, because Minus will be furious if and only if Daedalus jumps, the value of F takes its value from J, and that's all, right? So if J is 0, F is 0, right? If Daedalus doesn't jump, then Minus isn't furious. If Daedalus does jump, if J is 1, then F is 1, right? That's a deterministic standard equation. Here is something a little bit more complicated. So what happened with escaping? If J is 0, then E is 0. If Daedalus doesn't jump, then he will not escape. But if J is 1, then the Daedalus may or may not escape, which means that E can take the value of 0 or 1, right? And here is how I write that out. If J is 1, then E can take either value of 0 or 1. You can imagine it's just a set on the right side. But if J is 0, then there are just two values on the right side. I mean, one value on the right side, 0 and 0, right? So E is forced to take the value of 0, right? So if J is 1, E can take 0 or 1. If J is 0, then E will just take 0 on, right? And finally, Daedalus may but needn't jump. J is free to take the value of 0 or 1. That's all we know, right? The model doesn't tell you what he will do. It just tells you that he may do this one or this other action, right? Once you have the equations, then you have solutions of those equations, and those solutions describe the situation. So the solutions are all possible histories in the situation. So on the first history, he doesn't jump, he doesn't escape, Minus is not furious. On the second history, he jumps but fails to escape, and Minus is furious because Daedalus dies in the sea. On the last solution, he jumps, he escapes, and Minus is still furious. Right? So three possible histories. And you can also draw it as a graph. So you can see on the graph that E takes its value from J, F takes its value from J too. And I also note what values are possible in this model inside those little nodes. Okay. So once you have a causal model, you can talk in terms of causal model notions. So here is one. Phi is possible in M, that's how you read it. So some event phi is possible in the model if and only if phi is satisfied by some solution to the model. So for instance, it's possible that Daedalus doesn't jump and minus is not furious because J is 0 and M is 0 is satisfied by the first solution to the model. Right? And analogously, phi is necessary in the model if phi is satisfied by every solution to the model, right? So is satisfied by every possible history. So for instance, he jumps or doesn't escape is causally necessary because on every solution to the model, he jumps or does not escape. Right? There is more to that. There is a notion of undeterministic conditional independence. So it's an underdeterministic analog of probabilistic independence. It's very easy to understand once you really read into it. I will start with the unconditional version. So unconditional independence, every two possible events over x's and y's, over some variables x and some variables y, are co-possible. So every two possible events are also co-possible. If that's the case, then those events those variables are independent, right? So here's an example. E and F are unconditionally dependent, but they are independent once you conditionalize on J. Why? So they are dependent because if the Daedalus escape, you know that minus is furious. If I tell you that the Daedalus escape, that E is 1, then you will know that F is 1. Even though if I tell you that F is 1, you will not know whether E is 1 because there are some histories where F is 1 but E is 0, and there are some histories where F is 1 and E is 1. But if I tell you that E is 1, the Daedalus escaped, you will know, you can infer from that minus is furious, right? But once you conditionalize and use this more extensive definition, once you conditionalize on J, once you know what the value of J is, then you will not learn anything about E from the value of F, and you will not learn anything about F from the value of E once I tell you what the value of J is. Also, for those who are familiar with the causal literature, there is an analog of the causal Markov condition, which just means that the condition just states that every variable is independent from its non-descendants, conditional of its parents. So for instance, this case already illustrates that. So E and F are unconditionally dependent, but once you conditionalize on their parents, so you conditionalize on the parents of E, it becomes independent from F because F is not, is descendant. Like there is no arrow, there is no path from E going to F. Like F is kind of right outside of all the possible children and their children of E. Right, and so once you conditionalize on J, once you know what J's value is, F becomes independent from E, and that's an illustration of the causal Markov condition. And like lo and behold, the condition holds of under deterministic models. It can be proven. Good. Last quick thing: interventions to bring about this event. X is X, and Y is little y, and Z is little Z. Just replace the variables equations with X will take the value of X, Y little y, and Z little Z. And that produces a new model. So for instance, we have the old model of what may happen with Daedalus and minus. And if I tell you, okay, so let's imagine what would or could have happened if he didn't escape, or if he hadn't escaped, but minus were furious, then you will just ascribe 0 to E, 1 to F, and that will produce a new model, right? So you take the old equations, replace the equations for E with one that says let E be 0. You replace the equation for F with one that says F should be 1, and that gives you a new model. This new model has new solutions. right? And that's how it works. Good. So this is the underdeterministic framework. Equations can return many values, hence models can have many solutions. The framework affords causal modal notions of causal possibility and causal necessity, right? An event is possible if it happens on one possible history. It's necessary if it happens on all possible histories. And the framework also affords the notion of conditional independence, like probabilistic independence and the causal Markov condition. Even if this was a little too much, I mean, it's nice to know, but that it's hopefully the theory will be also understandable if you didn't very closely follow the presentation of the framework. So here is the causal decision theory, in case we don't have probabilities. So on this theory, an agent should solve a decision problem in 3 steps. First, to represent the decision problem with an underdeterministic causal model, where available actions correspond to values of some variable. So some variable represents the action of the agent. Once you have the model, you use the model to infer possible consequences of these actions. And once you have those possible consequences, choose an action whose possible consequences are no worse than the possible consequences of any other action. Before we get to the theory, what should means here, I intend the theory as a normative theory that tells you what you should do in this situation. But some people distinguish between descriptive, normative, and prescriptive decision theories. And descriptive is just a psychological theory that describes how we behave. This is not it. But a normative theory tells you what the right decision is. And the prescriptive theory can aid actual decision making. And if you really want it, I think you also could use this theory as at least in some cases, as a prescriptive theory. So a theory that would help agents perform or decide on actions in situations when they don't have probabilities. Right. Okay, good. So the general schema here is, let's say you have comparing actions A and B. So you build a model where the agent performs action A. You build another model where the agent performs action B. From this, you get all possible consequences of action A, all possible consequences of action B, and comparing those two possible consequences of one action with the ones of the other action, you can compare the actions, right? So let's go through the Dalus model yet again, right? Represent the decision problem with a model. We already had that. That's the model we built in the previous section, right? Then use the model to infer the possible consequences of these actions. So here are 2 models, and this is why I introduced those interventions, right? The first model says, okay, he jumps. He decides to jump. And the second model says, sorry, the first model says he doesn't jump. And the second model says he jumps, right? So you replace J's equation. In the first case, J takes on the value of 0, and that's all. And in the second one, it takes the value of 1, and that's all, right? And now you have 2 models, and those 2 models have their own solutions. The first model has only one solution. He doesn't jump, he doesn't escape, minus is not furious. The second model has 2 solutions. He jumps, doesn't escape, minus is furious, or he jumps and he does escape, and minus is furious. Right? Finally, choose an action whose possible consequences are no worse than the possible consequences of any other action. So in this case, we have 2 possible actions, he jumps or he doesn't, and let's compare them, right? So first, let's say that the Dalus cares only about escaping and nothing else, right? You have those 2 models, and you can visualize the possible consequences of those actions in the following way. The possible consequences will be just solutions to a model. So the first model has just one solution. He doesn't jump, doesn't escape. We don't care about minus. In the second case, he jumps and he escapes, or he jumps and he doesn't escape. Those 2 solutions are for him are equally good or equally bad, because he wanted to escape and he didn't. But in addition, the second possibility, and the second action, jumping, gives you this extra possibility of escaping. So it seems that on leximine, right, on just looking at the worst possible action consequence and comparing those. And if those are the same, then you go up and you check the second worst possible consequence. It makes sense for him to jump, because in the worst case and in the best case, if he doesn't jump, he doesn't escape. In the worst case, if he jumps, he doesn't escape. But in the best case, he jumps and he does escape, right? So it seems that he should escape. Notice that I cannot use any expected utility. You don't even have to speak in terms of utilities. You can just speak in terms of which solutions are better or worse, because there are no probabilities, right? We have to use stuff like maximin, lexemin. Good. So it seems that on the theory tells him, it seems the theory tells him that he should jump. In the worst case, the consequences are the same, but there is this extra option that is better for him if he does jump. Good. But say now Daedalus prefers escaping over staying in prison, which he prefers over dying. Right? He doesn't want to die at all. So in this case, we need a new model, because the previous model doesn't give us the resolution to think about this case. Right? Here's a new model. E is -1 if Daedalus dies, 0 if he stays in prison but alive, and 1 if he escapes. Right? And so those are the new equations. If J is 0, then E is 0. But if J is 1, then E might be -1 or 1. Right? So if he jumps, he either dies, and that's very bad for him, or he escapes, and that's awesome for him. Right? Good. And again, you have two models for those two possible actions. In the first one, he jumps. In the first one, he doesn't jump. In the second one, he does jump. Right? There are the first one has just one solution: doesn't jump, doesn't escape. The second one, he jumps and dies, or he jumps and escapes. And remember, now we said that he prefers escaping over being in prison, but he prefers being in prison over dying, right? So it seems that in this case, he would say, no, I don't want to jump. I want to stay in prison, because in the worst case, I'm still alive. In the worst case, if I jump, I will die, and I really don't want to. Okay. Well, I have 9 minutes. I will just. Yeah, I will quickly go for a Newcomb's problem. So there is a famous family of Newcomb's problems in standard classic decision theory. Here is an underdeterministic version of that. This is why I introduced this concept of underdeterministic independence. So here is just, I will just run over the explanation in terms of models. Here is what happens. You're predestined for hell or for heaven. And if you're predestined for hell, you will sin. If you're predestined for heaven, you will not sin. And also, if you're predestined for hell, you will go to hell. And if you're predestined for heaven, you will go to heaven. And the question is, should you sin in this case, right? Again, you construct a model, right? You're either predestined for hell or for heaven. If you're predestined for hell, then you will sin. If for heaven, then you will not. If you're predestined for hell, you will go to hell. If not, then you will go to heaven. Two possible actions. Right? You don't sin or you do sin, two possible solutions each. And here is how it plays out. I prefer sinning over not sinning because it's pleasurable, but I also prefer heaven over hell. And I prefer not sinning but going to heaven over sinning but going to hell. Right? I prefer the eternal pleasure over the short-lived pleasure of sin. Still, here is what the theory tells you to do, and that's the right solution. I think in this case, you don't sin. In this case, you do sin. So here are two solutions. If you don't sin and you go to hell, or you don't sin and you go to heaven. But if you decide to sin, it's a causal decision theory. So your decision is implemented as an intervention here. If you decide to sin, but you go to hell, then it's still a little bit better than not sinning, going to hell. If you decide to sin, but you go to heaven, it's better than not sinning and going to heaven. So it seems that theory says you should sin, because in the worst case, if you sin and go to hell. In the worst case, if you don't sin and you still go to hell. So it's better to sin and go to hell. Right? And that's a Newcomb's problem, because those are correlated, but really the theory tells you to do something that is negatively correlated with a good outcome. Right? Good. And that's the standard solution in Newcomb's. That's the proper solution in Newcomb's cases, or so people think. Good. So here is the theory that we want, that will give you those judgments that I just gave you. This is a little technical, just bear with me. There will be more figures with examples. So first, say that two actions are being compared and assume that any solutions are comparable. So for any two solutions to any two models, you can tell which one is better for the agent and which one is worse, or maybe they are the same. Right? And I would just call that a solution, the solution that is produced by an action is a solution that is possible if the agent were to perform this action, right? So this solution belongs to a post-intervention model. This is exactly what we did already in the cases that I presented. And I will say that a solution is unpaired if every solution produced by the other action under consideration is either strictly better or strictly worse. You will see how this works in a second. So which action is better depends on the following conditions, and you apply there. First, if some solution produced by one action is worse than every solution produced by the other action, the former action is worse than the latter. If C1 doesn't give you an answer, then you go to C2. If some unpaired solution produced by one action is worse than every unpaired solution produced by the other action, and some paired or unpaired solution produced by the other action, the former action is worse than the latter. Again, there will be illustrations in a second. If this doesn't give you a result, then you go to C3. If some solution produced by one action is better than every solution produced by the other action, the former is better than the latter. And if this doesn't give you an answer, then the actions are equally good. And the theory rationally permits the agent to choose any action if the four rules judge this action as at least as good as any other action. So here is how it works. Let's go back to the original. Either he doesn't jump and doesn't escape, or he jumps and either doesn't escape, or maybe he does escape, right? Those two solutions are equally good or equally bad for him. Right? He compares them, he treats them as equally of the same value, but there's one extra solution that he prefers, which was the one where he escapes, right? And the theory tells you in virtue of C3, if you C1 will not give you an answer, then you move to C2. It doesn't give you an answer, and then C3 will tell you that you should go with the red option, because in the red option you have this extra possibility. Here is another one, the second one that we tried, right? There is one pretty awesome solution if you choose red, but there is also a very bad solution if you choose red, and the worst solution if you choose yellow, the yellow action is better than the worst solution if you choose the red action. So Maximin tells you go with yellow, and this is also what C1 will tell you. Here is another one. The worst two options agree, but the second worst option is better if you choose red than if you choose yellow, right? So the worst options are exactly the same, so we kind of can forget about them. Then you jump to the second worst option, and the second worst option is worse if you go with yellow than if you go with red. If you run those rules, then C2 will tell you go with red, and it seems that's the right action, right? Okay, so the theory, what does it tell you? It tells you represent the decision problem with the model and actions with interventions, then gauge the consequences of those actions, and once you do that, and apply those criteria C1 to C4 to pick an action. Right? And I think the power of the theory partially comes from the fact that it can model many infinite cases. I will just show you those cases and what the solution is. I will not go through exactly like how you get there. Here is a simple one. So imagine there are like infinitely many. Maybe you're like choosing between, real numbers that are more than 10 and less than 10, and there are infinitely many of both. The higher the number, the better, right? If you go with yellow, it will give you a random number 10 up. If you go with red, it will give you a random number 10 down. It seems that you should go with yellow, and this is what you get, even though maybe you cannot even ascribe probabilities to that, right? the theory will tell you in this case, so let's say, for instance, all numbers below 0 are equally, both yellow and red, choosing yellow and choosing red may give you those numbers. But if it's a number that it's above 0, then let's say the red choice will give you from 0 to 20, and the yellow choice will give you from 20 to maybe infinity, right? That's how you read it. So there are infinitely many possibilities here, but if it's none of them, then the red possibilities will be worse than the yellow possibilities, and the theory will tell you go with yellow, right? And in this case, theory will tell you go with red, right? So infinitely many possibilities that are equally good or equally bad, either on yellow or red choice. But if you go with the red choice, then you might get those extra benefits. Here's how to read it. Here is a smaller set of options, both infinite, but you should go with yellow, right? Because the worst case here, or the worst cases here, are better than worst cases here, and so on, and so on. For instance, in this case, if those two choices give you exactly the same possibilities, even if there are infinitely many of them, the theory in virtue of C4 will tell you that those are equally good options. Right. There are a little bit more examples, but I'm running out of time. Okay, good. So this is pretty much it. Just to repeat, the motivation, we need a new causal decision theory in case we don't have probabilities for many reasons. There is an underdeterministic causal framework that we can use that has those notions of causal necessity, possibility, causal modal notions, and whatever you want from a causal framework. Once you have the causal framework, you can use it to provide this theory, and the theory is basically an extension of Lexemin, a little bit more advanced Lexemin that uses this underdeterministic framework. Theory is nice because it delivers the correct results, both in standard finite cases as well as infinite cases. Yeah, and that's that. Thank you very much.
Thank you, Tom. So, Óscar, is your turn. You have 15 minutes. Your comments, please.
Yeah, great. Thank you, Afra. Thank you, Tom. Again, I'll say it in public. I'm sorry I didn't send you the notes before. I was very, very busy.
Oh, yeah, no worries. It was enough time. No, it was very good.
Okay. So I think I'm just gonna read them, actually. So I just wanted to say a few things, right? The first one is that I liked it a lot. It was, once that you go past like that barrier with the formalism, it's very easy to understand and straightforward. So yeah, I liked it. Yeah, that's like the compliments part. Besides that, well, I understand that there's a normative theory, right? I also understand that decision theories are usually very demanding on agents, so it is hard to argue against the rules you propose on ground similar to those. So the rules are C1 to C2, right? But what makes your first rule plausible? It's the one that said, if some solution produced by one action is worse than every solution produced by the other action, the former action is worse than the latter, right? So the question is, can a very good solution produced by one action compensate for the badness of that action's worse solution? So like in the diagrams you showed us, you had examples like action one produces a solution like here, right? Oh, my cat. And action two produces a solution, a couple of solutions distributed in like this way, right? So you should choose this one because like the lesser evil, right? The worst case here is worse than the worst case here. However, what if like the best case here is somewhere over here, right? That's the question. Wouldn't it be like plausible to think that this is actually the better action? So that's one question. I don't know how you want to do this. Do you want me to like ask all the questions and then you answer, or
Yeah, I think you should ask all the questions because actually I added some slides, so I can just go through them. It will be easier for me.
That's great. That's great. So the next question was, isn't the second conjunct of the antecedent of C2 redundant? Because the first conjunct seems to imply the second, unless the second part is telling me that there is another object, right, with those characteristics. So you're telling me that there have, yeah, unless there are two solutions. Where is
I will go, no worries, I will go through it. So you can just, yeah, it will be on the, I have slide with that. So
okay.
Yeah, it will be.
Yeah. I had another question about something you didn't present, like about the which thing. But of course, I'm not going to ask that because it wasn't in your presentation, and that's okay. But another more general question I had was whether or not your theory is meant to be complementary to like standard classical causal decision theory, right? In the sense that you use it for the intended cases you were trying to address, and you keep causal decision theory like in the back for the rest. Or is your theory meant to replace altogether classical causal decision theory, right? Those are my questions to you. And that's everything I've got to say. I liked it a lot, and that's it from me.
Okay, Tom, do you want to say something about Óscar comments?
Yeah, no, absolutely. Yeah. Can you see the slides? Yeah.
Yeah, but I think we can also see like your notes. I mean, you don't have notes, but like the.
Yeah, no. Well, where is this? Sorry. Yeah, it's the beauty of Zoom. How do I do this? This. Okay, now you should be seeing it. Are you seeing it? Yeah. Okay, good. You're seeing that, right?
Yeah.
Awesome, thank you. Good. So first of all, thank you for those comments. They were great, actually, and I will revise some parts of the paper exactly in response to those comments. That's very good. And yeah, and they were totally not too late. I had enough time to think about them. Good. So the first question. So the theory says that some solution produced by one action is worse than every solution produced by the other action. If that's the case, then the former action is better than the latter, but can the very good solution produced by one action compensate for the badness of that action's worse solution? So I was thinking maybe here will be a case. So first of all, notice that's a problem with lexemin or maximin in general, rather than my theory. My own theory. I mean, it's just like it's a problem for every theory that has lexemin. And leximax, so choosing, instead of looking at the worst solution, you can look at the best solution to the best possible outcome. It has an analogous problem. Then you could ask the opposite question and ask, hey, what happens if, there is a really bad solution, a very bad possible outcome, and wouldn't that compensate for some awesome possible outcome of this action, right? So I was thinking, you may be thinking about the case like that. So look at the case on the left. My theory will say that you should go with yellow because the worst possible outcome if you go with red is worse than the worst possible outcome if you go with yellow. But on red, there is this awesome outcome too, the first dot on the top. And maybe that will compensate, right? So you cannot do it. You cannot just look at that and say, you cannot compensate in any way if you look at the diagram on the left. But here is how I think it's possible to think about it. If in contrast or from the perspective, like if you look at all of those solutions, you think that the red best solution is really awesome, then you might think that, hey, like imagine those are like possible lottery outcomes, right? You can get $1, $2, or $3 on the first one, 0, 1, or $2 on the second one, but also like $1 million, right? $1 million. And what you can do is you can you can imagine, hey, maybe I really don't want to distinguish between $1 and $2 or $3. It's one and the same. And I don't want to distinguish between $0, $1 and $2 either. It's exactly as like, it's somewhere around $3, between $0 and $3. Let's treat it as just one solution. I take part in this lottery. If I take part in the yellow lottery, I will get something like $1 plus minus some, another dollar, right? But if I take part in the red lottery, there is either I get something around $1 or I get $1 million, right? And in this case, it seems that you should go with red, and my theory will tell you to go with red, right? So really, the solution here is, rather than modify the theory, is just if you're thinking in those terms of, if you take like a step back and look at possible outcomes, and you just clamp some of them together, the ones that they don't really differ very much, right? As into one solution or solutions that are like equi-preferable by you, and once you do that, you get this second diagram, and the theory will tell you, no, go with the lottery that gives you $1 million, possibly, right? Or possibly zero, right? Answer B, this was answer A. Answer B, actually notice that in the theory, you can only compare solutions. And so you can't really say this solution is so much better than any other solutions. I don't know if you can see my cursor. The distances between those balls, those little dots, they don't mean anything. The theory just requires you, it just says that for every two solutions, you have to be able to tell which one is better than which one, or maybe that they are both equally good. But you cannot say that one is like a lot better than the other one, right? The theory the language doesn't have resources to say that. So in a way, also like answer B to your question is you cannot ask this question in the context of the model because it doesn't give you a language to say, that some theory is like much more better, like much better than, like one solution is much better than the other solution, right? It doesn't tell you by how much, it just can tell you that it's better or worse, but it won't tell you. You cannot express that it's better, 10,000 times, for instance. Good. The second, okay, good. The second question, isn't the second conjunct of C2 redundant? So here is C2. If some unpaired solution produced by one action is worse than every unpaired solution produced by the other action, and that's the red part, some paired and unpaired solution produced by the other action, the former action is worse than the latter, isn't this conjunct in red, isn't that redundant? So here is a case actually where you need this extra conjunct. So if you didn't have this conjunct, if we deleted the red part, here's what you would have. If some unpaired solution produced by one action is worse than every unpaired solution produced by the other action, notice that the single red, so the yellow solution is not unpaired, it's paired with the red solution. That's why the line, that's why the line is there, right? It says that the agent likes the yellow solution as much as the bottom red solution. But in this case, there is just one unpaired solution, it's the top one. And it is true that it's worse than every unpaired solution. It's worse than every unpaired yellow solution. Why? Because there are no yellow solutions, right? And that's the case where you need this extra conjunct. And yeah, it's unfortunately just to handle those weird cases. Maybe there is some other way to handle those. But this was, I consider like 20 different versions of this whole theory. This was the best way to handle cases like that, right? So really, this just comes in play where on the yellow side, everything is paired, right? Another case like that is where there are many more paired solutions, so yellow solutions, but all of them are paired, right? That's why you need this extra thing, and it's also worse than some paired or unpaired solution, right? Because in this case, the red one is not satisfied. If you get rid of it, then C2 will tell you go with yellow, and that's not the solution to this case, right? That's not the right action. You want to go with red. Good. And lastly, is your theory meant to be complementary to causal decision theory, or is it supposed to replace it? Very good. Good question. Whenever you have or care about probabilities and utilities, you will use classic decision theory. But either when you don't have probabilities or you don't want to use them for some reason, then you're totally, then you will use mine. So you're totally right. It's complementary. Sometimes maybe, you know, if you're very low on resources, so you have to very quickly judge some situation. Maybe it's possible to calculate probabilities, but you really, you know, you're just deciding whether to cross a street. And you think like, okay, if I cross the street now, I may die or may cross the street, but if I don't cross the street now, then I will not die. And that's all you need to make this decision. You don't want to die. Dying is very bad. You will decide not to cross the street. You don't want to calculate probabilities, right? So in this case, it seems that my theory will work even if there is some, you know, better and more some better probabilistic solution. But just because you don't have time to use that one, you will probably behave in a way consistent with my theory, right? But again, you're right. The moment that we have probabilities and we have all these other, all those other assumptions satisfied, then you can use standard decision theory. But if you don't, then you use mine. And again, thank you for those comments. They were very good, and I already know like how to change my paper a little bit to make it clear, given your comments. Yeah, thank you very much.
Okay, thank you, Tom. Thank you, Oscar. So it's time for the Q&A section. If you have any question, please raise the little hand with the icon in Zoom.
Good. Let me just get, I have headphones, I'm listening
yes,
to
yes.
it. Let me just get some water. Are you guys?
Jair. No sé si es Jair o Jair.
I think you're muted, so maybe that's why.
I got a question. Can this model be used to explain the multiverse or the theory of the multiverse? Because that was the thing that come to my mind when you were telling us this theory.
Okay, good, nice. So the decision theory, obviously, like the decision. Sorry. So what do you mean? Can you say a little bit more about the multiverse?
Yeah, the multiverse. I see the multiverse as a multiple options taking in different realities, some sort of thing. I think. I don't know if it's related with this or it's something else, but that thing comes to my mind.
Okay, good, nice. So here is because I know very little about physics in general. Probably here is the closest thing that I can kind of confidently say that maybe it works, and then you will tell me if that's close enough. So forget the decision theory and just focus on the causal part. There are theories of the universe expanding where so it's called some kind of cosmic inflation or something like that, where during some undetermined period of the universe, so it's not like it's causally undetermined how long it will go for, and during this expansion there are very many kind of packet universes are seeded. So within the general universe, you guys are recording that. I wish you weren't, because I might be saying something completely stupid. But let's trust me for the next 5 minutes, and then you can consult Wikipedia. So during this expansion period, you can see multiple packet universes, and those universes might differ in their physical laws. Like imagine, maybe the gravitational constant is all different in different universes. The problem with that is that there are infinitely many of them. No universe is more or less probable than any other universe, and therefore you cannot ascribe probabilities to them. All you can say is that it was causally possible for those universes to happen. And when you have a cosmic theory like that, so you have a theory in cosmology that posits those infinite universes, and it also says that, look, there are infinitely many of them, they should be all equiprobable, we cannot ascribe a probability function to those, then you can use my theory to say, oh, it's causally possible. No, they were causally possible because they happened, which means that the theory posits that they happened or could have happened, right? But you cannot ascribe probability, so you cannot use the standard probabilistic causal theory to describe them. You still can say that the Big Bang or whatever, the beginning of the universe was a cause of some of those pocket universes, right? Because if there was no Big Bang, then those pocket universes wouldn't have happened. But it doesn't. You don't need probabilities to say that. Now, if something like that is possible with like the multiverse, maybe, right? If you like think about our minds as being like some quantum machines, and maybe each time you like decide, then there is someone, there is you who chooses the apple, and there is also a you who chooses the banana, and the universe splits or something like that. If there are no probabilities ascribed to that, then you will use my theory to decide that, and you could use, I guess, my theory to think about those decisions, right? But again, I would have to think about that more. Basically, the hallmark is every time that it seems that you cannot ascribe probabilities, then you still probably can use my theory, but you cannot use the standard decision theory. So if your question was about a situation like that, then I would say, yeah, you can use my theory, but you cannot use those other theories. And that's like an extra benefit of my causal decision theory. Thank you.
Thank you.
Is that helpful? Hello?
Yeah, I mean, it's a super weird thing, and I'm really into that. So
I
don't know. That can come to my mind when I was listening.
Okay, nice. Thank you. I mean, you can shoot me an email if you think that there is some good application of my theory to that, and I would just have an extra reason to support my theory over other, like just justify my theory, because this is the typical comment from a reviewer is like, okay, all is nice, but why can't we just ascribe probabilities everywhere? And then I have to, there's always like 1 or 2 pages of like, oh, look, here are all those cases where you cannot ascribe probabilities. Yeah, so the more cases I have, the better for me. So I will look into that.
More questions? No? Okay. Tom, do you want to say something more?
No, I think that's that. Thank you very much for inviting me. Yeah, I actually have been to UNAM I went for a different conference, so I really like your university. I'm very happy to have been presenting here, even though it's online, because I would love to be there. I think your university and your institute is amazing. I love this place. So thank you again for this option of presenting, even though it's Zoom. Thank you. And thank you, Óscar. Those are really good comments again. I really enjoyed them.
We have a break of 15 minutes. Yes?
Yes, we're going to have the last speaker at 4:45. So we have a break right now. Brian, ahorita vamos a receso.